Right. So today we're going to learn about the NeurIPS 2023 dataset and benchmark struct paper, Temporal Graph Benchmark for Machine Learning on Temporal Graphs. And as you know, Andy Shenyang Huang will present it. He's a PhD student at McGill University and at Mila. He looks at temporal graph learning and is supervised by Raihane Rabbani and Professor Guillaume Rabousseau. And yeah, he's interested in representation learning on temporal graphs, in anomaly detection, in graph representation learning. And he was the organization chair for the temporal graph learning workshop last year at NeurIPS. And he will be for this year's temporal graph learning workshop as well. His previous research includes change point detection on temporal graphs, COVID disease modeling with temporal contact graphs, and also link prediction on temporal graphs. He also has some Medium blog posts also about temporal graph learning. Yeah, that's it. Is Farima also going to present? Because then I will introduce her as well.
No, it's just Andy. Thank you.
Okay.
I think I will present for today. All right, so thanks for the kind introduction, Julia, and nice to see everyone. So I will start sharing my slides. Oh, so let me share the link to the slides for anybody who joined later. And then I will share the screen. Do you all see my screen?
Yes.
Okay, good. Yeah, so thanks a lot for coming to my talk today. I'll be presenting temporal graph benchmark for machine learning on temporal graphs. And you can find the links to the website, the paper, the pip install documentation, and so on here. And this is a joint work. This is a joint work between different universities and institutions. So it's between me and Farima, and then Jacob and Matthias Fei, Weihua Hu, Emmanuel Rossi, Yuri Leskovec, Michael Brownstein, my supervisors Guillaume Rabusu and Rehane Rebane. And I will first discuss the outline of the talk for today. So I will first go over the background of temporal graph learning, give a little bit of the motivation of the work, and then give some overview of the methods and so on. And then we'll dive into the benchmark itself, how the data set is structured, the results we get from benchmarking different methods on both the link and node task, and then discussing the experimental results. So as a very short introduction slide, because we are the temporal graph reading group, we know that many networks are temporal. So on the visualization you see on the right is the Canadian Fly Network on April 2nd, 2020. And many of these networks change significantly over time, including social networks, traffic networks, financial networks, political networks, interaction networks, and more. And in general, there are two large categories of temporal graphs as defined in a well-known survey early on in 2020. So there is the discrete time dynamic graph and continuous time dynamic graph. And in this work, we'll be focusing on the continuous time dynamic graph, more specifically on the streaming setting to set as the standard of the evaluation that we consider. And you can find more details about the settings themselves in Appendix C. Okay. So to quickly define some notations, so here we are dealing with continuous time dynamic graphs, where this is represented as a timestamped edge stream, where the temporal graph G is defined as basically a sequence of edges, each have a timestamp. It can also contain node features and edge features, which some of the data sets in the benchmark actually contain can contain both node features and edge features. And in the streaming setting, the assumption is that previously observed test edges can be accessed by the model, usually for the usage of updating the memory of the model, but no backpropagation and weight updates can be performed with the test set information. And also feel free to stop me if you have any questions or raise your hand. Okay, now I'll give a very quick overview about the temporal graph learning methods that we benchmark in this work. So I'll break them down into two big categories. One is node embedding based methods, and the other ones are edge embedding based methods. And the node embedding based methods tend to use a GNN or some variation of it and generate embeddings for each node. And the edge embedding methods focus on directly generating the embedding for the edges. And these are two parallel category of approaches. And all these methods will be benchmarked, and we'll see the results later. And most of these work focus on link prediction, and there's relatively few work that study node level tasks in temporal graph learning, which is one of the motivation for this benchmark to include both link and node level task, and to see how the method performance will change between these two different task categories. And in terms of existing data set, here's a snapshot from our last year's paper, which summarizes a lot of the temporal graph learning data sets and benchmarks. So we can see that almost all the data sets have only 1 or 2 million edges at most, considering that temporal graphs can have many, many timestamps, and having a few million edges distributed across these timestamps means that these graphs are relatively sparse or are very small in size. So the limitation here is the small scale of the data sets. And real temporal graphs that happens every day, such as social networks and so on, can have tens or even hundreds of millions of edges. Now, now we'll also quickly look at the existing link prediction evaluation procedure. So the standard setting that most work follow is to look at the edges in the test set, and then these are considered the positive edges, so the edges that do exist. And then you take each of these edges, and then you would randomly sample one negative edge per this positive edge. And then you would use the AUROC or average precision as the metric for link prediction. So the problem with this is that, first of all, like in the real application, you don't have a class balance, right? So there's no guarantee that you will have one negative per positive. And the case is that for the most cases, you're gonna have a lot more negatives and a lot more queries that may not result in edges than the real edges that you have. And also another problem is that the negatives are sampled randomly. And we show in previous work that the randomly sampled negative edges are actually very easy to deal with because real-world graphs are very sparse, and the edges are usually focused on a small set of space, like in the node pair space. And by just looking at the previous edges that you have seen in training, you can already deal with many of the randomly sampled negatives and claim that they are not true edges. So that's why the random edges are usually considered to be more easy. And the OROC metric is usually limited to class balance case, which is the case for the standard setting. But as we know that a proper evaluation should contain more negative samples. And also some other problems, including that the negative samples are not consistent across papers. So so usually they are generated on the fly and not stored. Thus, the numbers from the papers can vary. And And also, most of these methods already achieve very high performance on the benchmarks, as we'll see. And that would appear that the problem has already been solved, which we show in this work that actually a lot of the performance of the methods are not even close to being 100%, as shown in the previous work that we'll see right now. So so first we'll look at the ORAC performances of the methods. So so in this table here from previous work, you can see that many of the methods are above 95% or at least above 90%. And it shows that all these data sets seem to be performing really well for all the methods. So that is a problem because it's very difficult to tell apart which methods actually perform better. That is also the case for the average precision performance. So this is from a recent work from last year. And you can see that on the Reddit and Wikipedia dataset, for example, the performance of the state-of-the-art one are around 98.4, like even 99. And these high numbers make it very difficult to tell apart the methods. So here are the three main motivations for building this temporal graph benchmark. So first of all, there's a lack of realistic and large-scale data set that can be directly applied in the industry and in real applications. And then second, there's a lack of standardized evaluation similar to the OGB does for the static graph for temporal graphs. And third, the existing high performance of methods on the standard benchmark really reduces the ability for you to differentiate the methods and tell how the method improve upon the state of the art. Okay, now I'll go into the description for the temporal graph benchmark. So the idea of the project is to build an OGB-like benchmark for temporal graphs, where we would provide the data sets, the data loaders, and the evaluators, as well as a leaderboard. So you can take your temporal graph learning method and then just run our code to get a data set, and then apply your method during training and test them with the evaluators. And then you can submit your results to the TGB leaderboard to be compared on a public leaderboard. So currently our data sets are large scale and realistic and come from 5 different domains. And in the benchmark, we cover both link and node property prediction tasks. And the TGB package, which is available on pip, and you can find a GitHub page as well, automatically downloads data sets and process them in NumPy, PyTorch, and PYG format. So you can choose and pick which of them fits better with your existing code base. And the evaluation is handled by the evaluator, which is reproducible and realistic. For example, for link prediction, we would actually store the generated negative samples. So all the performance evaluation will be compared against the same set of negative samples to guarantee consistent comparison. And we also have a public and online leaderboard to track recent developments. Okay, here is a bird's eye overview of the TGB dataset and the scale that we handle. So here, the x-axis is the number of nodes, and the y-axis is number of edges, and the size of the circle is the number of timestamp. So we can see that existing data sets are usually smaller in scale, usually by 1 or 2 magnitudes smaller, as well as not containing that many timestamps. In comparison, the data sets that we propose in this work are much larger in node, edges, and timestamps. Here are some statistic of the data sets. So here we show that some of the graphs are weighted and directed, and some of them also have attributes. And the domains contain the interaction network, rating network, transaction network, social network, and traffic network. And the data sets are further colored by small, medium, and large. And in each category, you can find small, medium, and large to start building your method on the small data set and then test it on the medium one, and then later submit to the large one. So this also opens opportunities for work that focus on scalability to test on really large data set that would have like, for example, 67 million edges or 72 million edges for the TGBR flight and TGBN token dataset. And here are more additional properties on the dataset. We also show that for the dataset that we present in the paper, they cover a diverse range of dataset properties. So here, I will mostly talk about the inductive node ratio. So this shows the percentage of nodes that are in the test set that are brand new that you haven't seen. So this is similar to the inductive setting used in previous work, where we in the previous approach, they will remove nodes from the graph and then reserve them as inductive nodes. While in this work, we show that because the size of the data set and temporal graph naturally have new nodes that arrive in the test set, actually a large percentage of the nodes for many of data set that's more than 10% for the link prediction task naturally have this inductiveness to the test set, so that your method must perform well on both transductive and inductive nodes in the test set. Okay, so here I will get into the first task of dynamic link property prediction. But before I do that, is there any question from the chat or the audience? Okay. If there's no question, then I will continue. All right. So for the dynamic link property prediction task, the goal is to build a general category of tasks that focus on predicting the property of a link at a future timestamp. For the dataset that we include for now, this focus on the link prediction task. However, this is a general link category, and we are planning to include additional data set that potentially have a different task than just predicting the existence of a link. And for the evaluation of this task, we are looking at the link prediction evaluation for a given edge, U, V, and T. So for node U to node V at time step T. And in order to evaluate for this edge in the test set, you would first sample k negative edges from the same source. So here you would fix the source node, and then you would sample k different destination node for time t. And then here we will sample half of the historical edges and half of the random edges. So the random edges are the standard approaches, and historical edges are basically the edges that you have seen in the training set, but you don't currently observe. So you might have some recurring edges over time, and at this step, it doesn't recur. But you still want to test on it because for many applications, such as flight prediction and so on, many of the edges will be recurring. So you would have a flight going from node U to V on Monday, Tuesday, but not Wednesday. But you still want to test if the method can understand that pattern on Wednesday, for example. And then by doing half and half of these two different types of negative edges, we can help see the method performs on both of these type of edges. And then the evaluation is by the mean reciprocal rank, which is the MRR matrix. This is a common ranking matrix in recommendation systems. And here you would rank your positive edge, the true edge that you would have, across all the negatives, and see if the ranking or the probability you assign to your positive edge is higher than all the negatives. Yeah, and then just a footnote that we provide all the negative edges for each of the data set for the link prediction task. And all these are pre-generated negatives. So when you download data sets, they will be downloaded automatically as well. Okay, now now I want to get into some observation we have on this task. So so now we have improved the evaluation procedure. Now we want to look at some performances and some results. So first, I want to discuss the surprise index, which is defined as the ratio of test set edges that you don't observe in the training set. So so in some sense, these are basically novel or inductive edges you have in the test set. And with a high surprise pattern, you can imagine that it might be more difficult for the models because they haven't seen these edges appearing before in the training set. And we see that for the TGB datasets, there are some datasets with higher or lower surprise index. And here is the effect of the surprise index. Note that here we put this in the appendix and we fix the number of negative samples per edge for a fair comparison. So we look at two different data sets here for the small scale data set on the link prediction task. So for these data sets, on the left is a data set with low surprise index, which is also a very commonly used Wikipedia data set from the TGN paper. And then we also have the review data set, which is a new data set that we propose in this work. And it has a very high surprise index. That means a lot of the edges are not seen during training. And we can see that the methods that perform really well on the wiki data set, such as like TGN and CAWN, actually have a very significant reduction of performance on the review data set. And also the best performing method, CAWN, have a drop of more than 50% on the review data set. So this shows that for a benchmark, it is good to evaluate on both the datasets with high surprise index and low surprise index and compare the best model from both of them. And also, we see that the edge bank, which is a heuristic that just stores all the previously observed edges and then predict based on if you see it before or not, can perform relatively well on data sets with low surprise index, but have much poorer performance on data set with high surprise index. And in fact, the performance is inversely correlated with surprise because the brand new edges just will not be predicted correctly for this heuristic. So that's the first observation that we have. For the second observation, we want to look at what are the effects when we play with the number of negative samples. So here, once again, we look at the wiki data set with the 20 negative samples on the left and with all the negative samples. Note that because this is the smallest data set we have, we are able to afford to test with all the negative samples. By all the negatives, we mean that we take a source of the positive edge, and then you just basically brute force all the destination, like test on all the destination that you can have. And then you generate the performance based on that. So that is a very complete evaluation. So when you go from just 20 negatives to all the negatives, you can see a very significant drop in performance from the same method, even on the same data set, right? So you can see that, like, for example, the DIREP and TGN both have a drop around 30% performance. And some of the best performing methods, such as like TCL and Graph Mixer, have a significant drop in performance. While the two of the methods, such as CAWN and NET, actually performs really well even when you are testing with all the negatives. This shows that they truly learns that the positive edges should be ranked much higher than any given set of negative that you have. And this further shows that in a standard evaluation, when you are just comparing with one negative, the results will be highly biased and make the problem super easy. That's why we see the very high performance from before. Right. So all negative. So there's a question from the audience. So all negative means that you basically take your positive edge, U, V, and T, and then you take the U, and then you evaluate on all the possible V that are not true edge. So that's what we mean by all negative edges. So basically all the possible destinations that don't exist. Okay. So now we'll also take another look at the training time and inference time, and a bit look at the scalability part of the existing methods. So just want to quickly note that the edge bank time is really fast because it's just a hash table and requires no training, and it's just a heuristic. So this is just here for comparison, but all the other methods are neural network based. So if you look at them, you can see that on the y-axis, it shows that on these data sets, the methods from different category can have orders of magnitude different training validation time as well as inference time. Now, this shows that there's a huge gap in the computational cost of running these methods. And then this will become even worse because these are only the smallest scale data set we have in the benchmark. So for the wiki and review, these are the smallest ones. And for the much larger ones, it becomes infeasible to run some of these methods. So we only keep the TGN and direct, which are the fastest that we see here, for the large scale data set, and leave the other ones as future work to be scaled up to the larger data sets and to put to be put on a leaderboard. Okay, so these are the large scale data set that we have in the link prediction task, with the largest data set being the flight data set with 67 million edges. And the blue one is the medium scale, and the green means that it's large scale data set. And we can see that on these data sets, for the most part, both direct and TGN can outperform the edge bank heuristic. However, on the coin data set, the edge bank has a second best performance on a test set. And also many of the previous methods are too expensive to run on these larger data sets. And one important direction is to either improve the code scalability or to design more efficient methods. Okay, now we'll get into the null probability prediction task. Are there any other questions from the audience? Okay, so I will go into the null probability prediction task. So the goal for this category of task is to predict the property of a node at a future timestamp. Note that this is still very different from the static prediction, because in the static task, you usually have one label for the node for the entire graph, right? But for temporal graph, the label of a node can also change over time. And you want to learn this dynamics of how the node interactions changes. So as a first attempt, we propose the node affinity prediction task, which essentially take a node perspective to focus on how the frequency of interaction or the preference of a user towards a set of items will change over time. And here we use the normalized discounted cumulative gain, or the NDCG metric, which checks not only just checks the ranking of the top method, like the top results, but also checks that if the top 10 items and the preference of the ranking of the top 10 items matches that of the ground truth. So there's a question from the audience. How much time does it take to evaluate with all negative mode for larger graphs? That is a very good question. Like unfortunately, currently it's not possible to run with all negatives on the large graphs. That's what we intended to do at the beginning of the work, but we realized that some of the method, like even the fastest method, can take weeks to run. So for example, just go back a little bit. For the flight data set with only 20 negative samples, so these are very large data set with like millions of edges. And for each of the positive edge, you will sample 20 negatives. On the largest one, flight data set, with only 20 negatives, it would already take more than 1 week to run. Yeah, so it's not possible to run with all the negatives because they also tend to have many nodes as well. Okay. And another question from the audience, I will also answer now. The sampling of the negative we are referring to is for the test set. So this is not for the training set. For the training set, you would do the standard training. So that's not the focus of the work. So, but I think it's a very interesting direction. So for the training, we still sample one positive per one, like one negative edge per one positive one, like similar to what's done in the previous work. But for the test evaluation, you would sample multiple negatives, because that's how you would apply the method in the real world. Okay, so let's continue. Now, yeah, so now going back to the node level task, and we are planning to add more node classification tasks and so on in the future. And if anyone in the audience knows about some large-scale node classification data sets for dynamic graph, you can also contact me. So the plan is to include more data sets and more task category over time. Okay, so here is a very quick look, but I won't get into too much of the math here. This is just for the reference, but the node labels that we generate in the work is essentially based on the dynamic graph structure or the temporal graph structure. So so basically for today, like for the label of today, you would look at the interaction for the node in the next 7 days or so, and then you would look at how frequently this node interact with some other genres or the items that you have in the graph. And then you would generate a frequency vector for that node. And then that's the node labels in this task. So the node label will change from each day as you kind of slide into the future. And you are always predicting the like the interaction in the future. So so when you are testing for today, you are essentially testing for like 7 days into the future, for example. Okay, there's more questions in the chat. For the validation set on the link prediction task, we also have the same number of negatives per positive, because the goal is to have the validation set basically kind of mimic the test set. Otherwise, the results you get from the validation set like would not make sense, as we see that with too few negatives, the performance will be very high. So it doesn't reflect the test set performance potentially. Okay, what kind of tasks are considered in node classification? Two class or multi-class. So this depends on the data set. So currently we don't have a node classification task in the strict sense, currently we have the node affinity prediction task, but we are looking into adding some node classification task data sets in the future. Yeah, so if you have the binary or a multi-class, will be depending on the data set that we have. And thanks for references to the data sets. If you can also send it to me over on the TG Slack, if you have access to it, or by email, that would be great. Just so that because Zoom doesn't track like the messages. All right, so I will continue the presentation. Now we'll look at some results on the node affinity prediction. Note that this task is different from link prediction. Like it is closely related, but this is modeling the user preference or the frequency of interactions. And this actually cares about all the classes, like all the destinations that you want to go to. Because, for example, if you want to look at how the user is listening to different music genres, you will care about the prediction for all the music genres equally. And you want to look at which of the top genres, like top 10 genres for the user, for example. We see that actually very surprisingly, some of the strong performing methods for link prediction doesn't really work well in the node affinity prediction task. Here we see that the performance is actually dominated for the most part by simple heuristic such as persistent forecast and moving average. Just to give some background, the persistent forecast means that you basically just predict the label that you previously see at t-1. And the moving average basically takes a moving average of the previous labels. And we see that these two heuristics actually performs really well. And on some of the data sets, like for example, the genre data set, the TGN has the second best performance. Like while on the other ones, they are close, but still there's like a lot of room to be improved in this task. I think this calls for the future research in more node-focused task and for node-focused methods, and to try out on these benchmark data sets. Okay. Now I finished the discussion about the main results from the paper, and I will go into some like some quick tutorial and installation guide. Feel free to also ask questions. Okay, there's another question from the chat. Can accuracy be used as metric for node classification instead of AUC and NDCG? So for the node affinity prediction task specifically, here we are looking to rank the interactions because you care about if the top 1, top 2, top 3 genre and their ranking. So the NDCG metric is more ranking-based metric, so it does make more sense in this case. But if you have a standard node classification task, then the accuracy can also be a good metric, or the AUC. So this depends on the node labels that you have. And like as we said, so we're planning to include more future node classification data sets into the benchmark. Okay. So here's the leaderboard on the TGB website. So so you can find the website following this link, and you can also submit to the leaderboard. And we already have the submission from the community on the leaderboard, and you are you are all welcome to submit for the leaderboard. Just maybe quickly, since we're talking about this, so how to submit to the leaderboard? So so you just need to fill in this Google form. You can also find this on the website as well. And here, the rule is that the validation set should only be used for hyperparameter tuning. And the test set is only reserved for testing. So you do not allow for any hyperparameter tuning, as well as backpropagation on the test set. And the submission form have all the details, but this requires a link to your paper and code for the proposed method for reproducibility purpose. Okay, so you can also install the TGB package very easily, and we also update and maintain it actively. So you can install the package by just doing pip install pytgb. This requires the the Python version to be bigger or equal to 3.9 to be installed correctly. And you can also find a lot of the tutorials on the tutorial page for the documentation website. So one example one is the link here. And you can see that it's very easy to run the TGB datasets. You're also welcome to use the dataset for your research for like data visualization or any other purpose. So you can just do from this import the link property prediction dataset, specify the name of the dataset, and then you can get the dataset object. And the terminal will prompt you to download. And we also have a documentation website for the API references and the tutorials that you just see. And you can follow this link here to go to the documentation website. And any suggestions on documentations and the website, you can also send it to me or raise an issue on GitHub. Okay, thanks to everyone for listening. And I will take some questions from the audience. So there's a question from Rosanna about continuous time dynamic graphs were formalized as a series of timestamp edge additions or edge removals. Do these datasets contain both edge additions and edge removals? So in our setup, and the most standard format is basically you have a continuous edge stream. By edge stream, I mean that you only have the edge addition events technically, and when the edges are not specified for a given time, you assume that it doesn't exist. So basically, the format that we follow is in the previous slide. Let me just go back a little bit. The problem formulation is here. So basically, you have this exact formulation. So you have a stream of edges that contains the source and destination. And then if the edge is not specified, then you assume that it does not exist. Hope that answers your question. And feel free to unmute yourself to ask the questions as well.
Just one quick addition. All of the method also, they don't distinguish between addition and deletion. So that's another point.
Yeah. So pretty much if you if the edge doesn't exist, then you assume that it has been deleted. Okay, and there's a question from the audience. And thanks for the kind words. There's two questions. Do you plan to add temporal heterogeneous network or temporal knowledge graphs in TGB? Yes, that's something that I would like to add. But since I'm not the domain expert on temporal knowledge graphs, I'm planning to work with some external collaborators to add the heterogeneous networks into the benchmark. And if you're interested in collaborating, feel free to message me on Slack or send me an email. Do you plan to add a leaderboard for the live update setting? I think this could be interesting for the long time spinning data sets to see the prediction performance for the models snapshot by snapshot and average over time. I think this is a very interesting idea. So actually, we discussed this live update setting early on in the work, and I think this has a lot of good industry application. The main reason that we didn't go with it is we want to focus on the continuous time dynamic graph for now. But it's true that if you have a snapshot-based graph, it would be very good to do the live update. And potentially this can be added as a separate category in the future. But there's no current plan to add the live update setting. But I think it's something that's definitely very good. And we are planning to continue adding and improving the benchmark. So yeah, so that's definitely something that's possible in the future. And also happy to collaborate on it. Okay, another question from Rosanna. So then if the source destination and time is in the stream, it means the edge occurs at t0. Yes, exactly. So for the S0, D0, and T0, it just means that the edge shows up at time 0. And if you want the same edge at time 1, then you will do S0, D0, and T1. That means that the edge reoccurs at time 1. Okay, and another question from the audience. If I consider temporal graph model like TGN as encoder, like any other static like method to give some embedding, can I use any decoder according to my task? Like no classification link prediction. Is it similar to the encoder-decoder form? I think this is true in a sense. So I think like if you look at some surveys on temporal graph, the standard formulation is to also have this encoder-decoder view for temporal graph. And the interesting thing about it is that because temporal graph is always changing and evolving, that means that the embedding you get from your encoder should always be changing. Now, you can do anything you want from the embeddings you get from the encoder, but you might want to be constantly updating it. And yeah, so you can check out more like more related work, and you can also see all the method references from the paper to get more idea about this. Yes, so this is very similar. All right, so so I will go to the one last slide. It's more like an announcement or like descriptions. So if you are interested in temporal graph learning, we have the temporal graph learning workshop at NeurIPS 2023. And actually, we are currently open for submission. The submission deadline is October 3rd, which is next Tuesday, I believe, and anywhere on Earth. So if you want to submit your temporal graph learning based work to the workshop, you are very welcome to. And also, we will also be in person at NeurIPS if you want to connect, and also at the workshop, of course. And this will happen on December 16th in New Orleans. And you can also contact the like the workshop email with any question you have. Yeah, let me go to I'll keep on this page and answer more questions from the audience. Okay, I think that's good. All right, thanks everyone. Feel free to post more questions on the chat. We still have a few minutes left. And yeah. And if you have any questions about like running methods or running the code on TGB, feel free to email me. And you can also raise an issue on GitHub. So if you go to the TGB GitHub, I don't know if you see the GitHub page, Parma.
Yes, it's visible.
Okay. So if you find any bug or any issue, you can create an issue here on GitHub, and I will get around to it. You can also just email me. And the newest version for the package is 0.9.0, which I just updated yesterday. And please use that version for the leaderboard submission. Okay. All right. Thanks, everyone. And yeah. And thanks so much for coming to the talk. And the talk will also be recorded and posted online. So you can always rewatch it if you want. Yeah. All right. Thanks, everyone.
Thank you very much for the nice presentation. So if there is no other question, I think we can wrap up here.
Yes, let's wrap up. and have a nice day. And for all of you that are submitting to iClear, best of luck with your submission. All right.
Thanks,
See you.
everyone. Bye.
Thank you.
See you. Bye.